So today we open a session with Laura Covi, who's going to talk about the cosmological implications of the neutron electric dipole moment. So Laura, please.
Thank you. Yeah. So hi to everybody. I'm very happy to be here, and I hope to tell you a little bit of a recent work which we did with the postdoc in Göttingen, Sarif Khan. But I will start first with a bit of introduction to, well, I guess I can go very quickly through it, but I had a few slides of introduction just also for the notation. And then I will go to describe a model. This model is a model where the Pechi-Quinn symmetry is not a global symmetry. It just appears as an accidental symmetry, and I will explain actually why. In order to obtain this symmetry, but still solve the strong CP problem, we need to add an additional U1 symmetry, which with particular charges. And this I will also explain how it works, so that actually we can suppress any non-renormalizable operator which has a contribution to the ADMs. Nevertheless, as I will show, there are actually contributions which can be substantial to the ADM, just beyond the corner in practically. I will also discuss if this type of axion can be the dark matter. And we will see that these two actually requests are a little bit in trouble, in the sense that the constraint from the ADMs forbid the axion dark matter, in at least for certain values of the parameters. And in that case, if the axion cannot be the dark matter in this model, actually we have a second candidate. And this in this case is a right-handed neutrino. And I will describe very briefly also what happens in that case. The interesting thing is that also in that case, the density of this candidate is actually connected to the parameters in the axion sector, and not really very much on the parameters of the neutrino. And then I will conclude with a few possible ways to see this type of models. Okay, so CP violation in standard model and ADMs. Well, the CP and T symmetries, I guess everybody knows what they are. They are connected, of course, to charge conjugation, the change of parity, and the time reversal. And of course, in quantum field theory, we also have an important theorem I have to mention, the CPT theorem, which states that, of course, if you have a Lorentz invariant QFT with Hermitian Hamiltonian, you cannot violate a CPT. This means, of course, that if you have CP violation, you have T violation, and vice versa. So, and this is an old theorem by Luders and Pauli. So in this case, of course, we are interested in CP, but of course, also T violation is automatically there. Now, the electric dipole moments are related to the charge density. And here is the classical definition of the dipole moment, which is practically the average of the coordinates R with the charge density rho of Q. And of course, if you go to the quantum mechanical, oh, sorry, but the rest of the slide is not there. Wow, why? Sorry, there is a problem with my slides. Yeah, things are missing. Oh gosh. Yes. Sorry, I think on my laptop it was looking okay, but yeah, sorry for that. Okay, so from the quantum mechanical point of view, then the electric dipole moment is connected to the wave function, and this is again the average of the coordinate weighted by the wave function, and usually it is actually parallel to the spin. But it has also different properties under P and T parity. So we have here, as you see, under the P transformation, the dipole changes direction, but not the spin. Vice versa, under the T transformation, the dipole remains the same. Instead, the spin changes the direction. So you see immediately that if you do both transformation, P and T, both of them remain the same, and this is a symmetry which is there, but you don't have the P and T alone. Of course, this is only one possible moment. If you do really the full Lagrangian for a fundamental particle like the electron, you don't have only the electric dipole moment, you have the magnetic, as usually you have the anapole moments, and all of those are generated by the radiative correction. Now, the electric dipole moment is particular because it violates CP or P, in this case, as we have seen. And in the standard model, if you want to violate CP, you need actually to have sufficient practically violation from the CKM matrix. And you don't need only one vertex or two vertices, you need actually 4 weak vertices, because you need also to mix the generations. And at the end, if you compute it, you need these 4 weak vertices, which of course are in part also suppressed. And you need, of course, higher loop level, so that if you compute the contribution, it is actually very small. It's of the order of 10 to the minus 33. So it's much smaller than the one which is measured. And this is also the hope that if, therefore, on any other contribution coming from new physics can give you a stronger contribution. And indeed, this is what happens in the model I will describe. Now, how is this connected to the strong CP problem? Well, this is also probably known to everybody. It's the fact that, of course, due to the non-trivial structure QCD, you have to add to the Lagrangian this additional theta term with the interaction with the gluon field. But and this term is again violating T or CP. And if you actually want to be more careful, you have actually also the CP violation from the electroweak sector. So the parameter is not only this theta parameter, but actually you have to include with it this argument of the determinant of the quark matrices, quark mass matrix. And in that sense, yes, it's actually not visible there, but this term is the one which contains the electroweak phase. So the parameter we will actually need to cancel is actually this theta bar, which is the sum of the two. And generically, usually you have this term. Well, this one is still missing. OK, this term generates actually also you can rotate it into the mass matrix of the quarks. And in that case, then it gives rise to a CP violating vertex for the pion, which generates then the electric dipole moment. And you see here the formula for the dn as a function of this theta bar. And exactly this gives the constraint that the theta bar has to be less than 10 to the minus 10 or something of that order. So this is one of the strongest constraints. And of course, the theta bar is expected to be order 1. So you don't have any reason to have such a small number. So one possibility to solve this problem is to make this theta dynamical. And this is the Peche-Quinn solution. So to have a pseudoscalar field which plays the role of the theta. In this case, you usually what you do is adding a global U1 symmetry, which is broken spontaneously at the high scale. I will say later on what is this FA, but it's of something of the order of 10 to the 10 GeV. And the only degrees of freedom which remains is the axion, which is the corresponding Goldstone boson. At the end is a pseudo Goldstone boson because you have actually a breaking of this symmetry. I will get to that in a minute. But this field is coupling to the gluons through a coupling of this type, which is exactly the same as the theta term I had before. So in that sense, then is theta plus this A field, which plays the role of the theta parameter. And yes, and in practice, the idea is that this field has no potential in the early universe and therefore can take any value. And the potential is generated only at the QCD phase transition when you have practically this cosine type of potential generated by instantons effect. And this potential has automatically the minimum, the cosine is always theta bar would be plus A over F. So at the end, you have a vacuum expectation value of the axion, which cancel exactly the theta bar. And notice that we will come back to this, of course, later, because the fact that the axion can be displaced from the origin in the early universe will also be the reason why you can have dark matter. So the energy density which is in this field will then remain into the oscillation of the field and will give rise in principle to a density of dark matter component. But for the solution of the theta problem, of course, these oscillations are not important. The important thing is that you have the minimum of the potential exactly at the zero. And there, in some sense, is your vacuum expectation value. But this is the generic solution. But what happens actually if the Pechet-Quinn symmetry is not a global symmetry? And this is actually one of the big issues for global symmetries generically in model building, since we do not believe that gravity actually keeps these symmetries or respects these symmetries. There is no reason. There are arguments based on wormholes and other also black holes, and the fact that there is no conserved charge. So it's practically not possible to really define properly a conserved charge. So we believe that gravity can actually violate any global symmetry. Instead, of course, this doesn't happen if you have a local symmetry. So this means that actually you would expect to have possibly additional operators which do violate the Pechet-Quinn symmetry connected with gravitation. And this one was an old idea. So actually one of the first paper I know of is from Kamienkowski and Mantrasser already in '92, when they pointed out that this type of corrections are actually there generically, and in some sense they have to they can play a role and change actually the axion potential. Now, in another idea which is also all around since long time is to actually use another symmetry to protect, in some sense, the Pechet-Quinn symmetry. And this symmetry has to be local if you don't want to run into the same problem as the Pechet-Quinn symmetry, but it doesn't have to be the same as the Pechet-Quinn. So in the model I will show you, we will have indeed a U1 symmetry which is chosen in such a way that most of the operators which violate the Pechet-Quinn symmetry are suppressed. And but still, the Pechet-Quinn symmetry is not a full symmetry, but it's only an accidental symmetry for the low energy operators of the theory. And in some sense, the Pechet-Quinn symmetry becomes a purely accidental symmetry, which is similar to the case of the baryon number or the lepton number to the standard model, because also there is no reason why the baryon number or lepton number are conserved. It's only that if you write down their normalizable Lagrangian for the standard model, you don't have any operator which violates them. And of course, if you go to higher order operators, for example, dimension 6, for the case of proton decay, of course, you can have operators which do violate proton decay. Yeah, so this model we proposed earlier this year is actually an extended KSVZ model. So Kim, Schiffman, Weinstein, and Zitnitsky model, where the role of these exotic fermions is actually played by many fields, and we have two sets of different exotic fermions. We have to add an additional U1 with which we break at the same time as we break the Pechet-Quinn symmetry in some sense. So we have additional charges also for the standard model fields under this symmetry, which are given here. And this U1 Pechet-Quinn is the nominal Pechet-Quinn charge, which you see here. We also give in some kind of Pechet-Quinn charge to the electron and the lepton, the first generation. In some sense, one of the neutrinos as well. And this plays actually a particular role later on to be in an additional dark matter candidate. So that's why the charge there is a little bit different. Otherwise, we could have chosen also the same charge as the other, but then we lose in some sense the role of additional dark matter candidate for that field. And the important part are the exotic particles. So we have two sets of fermions, which are not charged under the standard model group, apart from the colored group, of course, in order to give you the anomaly for the axion. And we have here n chi and n psi copies of these fields. And we have also two scalars, which are related to the breaking of the symmetry. We need two of them, first of all, because of the different representation of the fermions and in order to give mass to all these additional exotic fermions. And secondly, because we need one field will be the Goldstone boson, which is absorbed by the gauge field in the additional U1. In the second pseudoscalar will be really the axion. So at the end, well, first of all, the charges are actually fixed by anomaly cancellation of this U1. You maybe also know that actually in the standard model, there are not so many anomaly-free U1s that you can write down. I mean, there is U1B minus L and a few other cases. If you add these additional fields, of course, you can arrange this U1 to be completely anomaly-free, but the charges are related. And here I give you some of the solution of these charges. These charges depends on these parameters Z, Y, and chi, which is the number of chi field with respect to psi fields. And as you see, we were able to find one rational solution where all the charges are rational and practically multiple of these alpha R, which can be chosen completely practically arbitrarily, and at the end, and nothing really depends on alpha R. The only thing which is really important are the ratios of the charges. We will see in a minute. You see that I am taking a lot of fields here. We are taking here 10 or even more fields of exotic fields, and it will become clear why in a minute. So as I said, the axion is actually again one of the combination of the pseudoscalars. So of course, when you break the symmetry, you can write the scalar fields as the usual scalar component and the pseudoscalar part connected to the angular degrees of freedom. And in practice, here I write the combination which becomes the axion. The orthogonal combination will be the part of the Z boson ZX, if you want. And this axion has a coupling to GG dual, which is exactly coming from the diagram, the triangle diagrams, which is exotic fermions, which I didn't draw here, but this is the Lagrangian that you can obtain when you integrate out the exotic fermions. And you see that practically the role of FA is played by this combination of the vacuum expectation values, and this n psi can play the role of the domain wall number in the usual models of axioms. And notice that therefore, if you take n psi equal to 1, you have no domain wall number 1, so you have no problem of domain walls in the model. Okay, and secondly, let's come to these additional gravitational terms. As I said, the Peche-Quinn symmetry here in this case is accidental, so we don't take it as a global symmetry. So you can have operators which violate the Peche-Quinn symmetry, but they don't have to violate, of course, the U1x symmetry. And this constrains a lot what you can do, because, of course, these U1x charges are a bit peculiar in the sense that there is yes, practically you need a non-trivial powers of the fields in order to get really a singlet under this U1x. And in particular, the first, the lowest dimensional operator you can write down with for the scalars is this operator, phi1 to the n psi and phi2 to the n chi. If you go back to the charges, you see that this combination is actually always a singlet because of these anomaly constraints. In practice, this field has a yes, so the relation of the charges are such that this sum here is exactly giving you 0, so that you are exactly in a singlet. And you see that since you have here a power of n psi plus n chi fields, you need a corresponding suppression of the Planck scale. And this suppression is the one which really suppresses also the contribution to the electric dipole moment. And that is why you need a large number of fields in order for this operator to be a sufficiently high order. Now, if you look at this operator, you can see immediately due to this Hermitian conjugate that if you write here inside the fields as I wrote them here, you obtain actually terms which have exponential of combination of the axial field, the pseudoscalar fields. And at the end, this leads to the potential which has this form, where here in front you have again a kind of new mass term, which is related to the vacuum expectation values here. And here I rescale it by the FA, which I defined in the previous slide. So that at the end here, in this case, I get again a cosine potential, but I have here a different coefficient P, which is connected again to the number of fields, and a delta, which is the shift from the 0. And this delta is related to the imaginary part of the coupling G. So we need indeed also an imaginary part of G in order to have a shift. But generically, there is no reason why the coupling here has to be real, so that at the end, this will give you to a shift of the minimum of the potential away from 0. But suppressed by this power of the Planck scale and the wave of the fields. So here is the contribution to delta theta. So delta theta is exactly the shift that you have in the potential. And this again, it's the order, so if you want, of the scale of the mass scale given by these two operators. And luckily, due to this very strong suppression by M Planck, it can be actually very small, even if the vacuum expectation value here are relatively large. Of course, as usual, we have also in this case the usual bound from astrophysics telling us that this FA has to be larger than something like 10 to the 9 GeV. And therefore, this V1, V2, we will see later, they don't have to be both of that size, but actually one of them can be larger. But usually in FA, so this one is also something I forgot to say. If you look at this expression here, you see that when one of the two waves is larger than the other, then the role of FA is played by the smaller wave. And the other wave in principle can be much larger, but it doesn't change the value of FA. So at the end, in some sense, the constraints from astrophysics give you a kind of lower bound for both of these V1, V2, and while one of the two, though, can be actually larger. And here, of course, is the usual constraints. So you have something here, the limits from astrophysics. So if you impose those constraints and you look in the parameter space, what happens, you find actually that there is still a room for the ADMs. And this is actually shown in these plots. Here they are done for different values of a field. So here we have nk equal to 9, and here nk equal to 12. We take always the number of psi field to be 1. Notice that actually the system at the beginning is actually symmetric. We could also exchange chi and psi, and taking a large n psi instead of large n chi, it's practically equivalent. You just have to exchange the roles of the two fields. So it's not a new type of configuration. And in this case, you see that in the red region, we are just below the bound of the ADMs. So in this case, for example, we can get there. We have a vacuum expectation value here, V2 of the order of 10 to the 11. V1 can be much larger. And this is in this case, again, because we took nk to be larger. So the delta theta is much more sensitive to V2. Here, nk is large. So V2 is the one who played with the strongest role in delta theta. And so this, in principle, this plot, of course, can go on. So on this region, and if you want in the red region here, we are just one order of magnitude within the present bound of the ADMs. And of course, if you go and suppress the V2 stronger, you get down and you have a value which is very small. And as I said, you can have it also so smaller and smaller. In the case of the 12 fields, the figure is similar, only that you move to larger value of V2. And this has a consequence later on for the dark matter, because of course, we do need actually the wave to be sufficiently large to obtain the sufficient density in of the dark matter. The neutrinos. So in this model, I actually don't have any slide on the neutrinos. I decided not to put them, but the neutrinos, we have also chosen the symmetries and the charges in such a way that we have the operators, the usual seesaw operators for the neutrinos, only that the ones who give the mass of the neutrino are actually, again, non-renormalizable operators. And therefore, those are again depend on the wave of the fields phi1, phi2. So in that sense, the mass of the neutrino is again related to the vacuum expectation value. That's why you have these lines. And here we choose one value of the Yukawa coupling of 10 to the minus 3 to get these lines practically. But you see that you obtain here, due to this non-renormalizable operator, the masses of the right-handed neutrino are in the GeV, TeV scale. Of course, you could go on in this plane and you take a larger Yukawa here, or move further in the plane, and you can get them also heavier. But you tend to, since it is coming again from a non-normalizable operator, the neutrinos don't have a mass of a scale Fa, but of a value much lower than Fa. Yes, so this is one of the other things we require the model to do to give us the right-handed neutrinos with the right mass to give then the light neutrinos masses. Okay. Now, yes, so can this axion be a dark matter candidate? Now, for the case of the dark matter, we produce it usually through this misalignment mechanism. This means that we produce it proportional to the theta angle, the initial theta angle, which we take usually to be order 1. And then the scale, which really determines how large the density is nothing else as this FA. So the question is if we can get to FA large enough, and usually we need something of the order of 10 to the 12 to get sufficiently large omega A. And unfortunately, we cannot always produce enough dark matter. So here are the two plots for nk equal to 9 and nk equal to 12. So for nk equal to 9, actually in the old parameter space I shown you in the previous plot, FA is always too small. And this is due to the EDM constraint, because we see it here. Here the V2 is always lower than 10 to the 11 GeV. And this means that FA is dominated by V2, it's practically equal to V2, and that means the energy density in dark matter is always too low. Instead, of course, here we can get to larger values. So for the case of 12 fields, we can get to omega h square of the order of 0.1. So in that sense, we can obtain this field to be also the full dark matter density, but at the cost of having more fields, let's say 12. We need 12 was the minimal number of fields we were able to find a solution with full dark matter density in the axion. For number of fields less than 12, we had always too few. So the density was always too small. Of course, you could compensate the smaller density with a larger misalignment angle or things like that, but we didn't really push that. That would be another possibility. And in this case, we were actually looking mostly at the case where you have theta for the one for the misalignment angle. Now, what is another consequence of having too many colored fields? Well, the issue is a little bit that, of course, asymptotic freedom is in danger. And you have here that these fields, these additional fields contribute to the beta function of QCD. They are all colored. And if you write down just the usual beta function, you have the 7 here, which is the contribution from the standard model. And the additional fields are giving this contribution, which is, of course, opposite sign, and can cancel also or overcome the standard model contribution. And indeed, you can easily check that it actually changes sign is the total number of fields is larger than 10. So that is also why in the previous plot I was concentrating on 9, because 9 chi fields plus 1 psi field will exactly correspond to the 10 fields. And in that case, we are still in some sense keeping the asymptotic freedom. But if you go to the 12 plus 1, 13 fields, like in the case where you have dark matter axion as a dark matter, then in that case, you have to give up asymptotic freedom. Of course, I mean, these, of course, also these additional fields enter in the running only at the very high scale above their mass. So this means that this change of the beta function is far away, and it could also be modified by additional other fields. But in principle, of course, adding so many color fields does have a role and put in some sense, if you want, in danger also unification of the coupling and so on. Yes, in principle, you could think about models where you try to correct that again back to a unification, but it's one of the things that this model, as I said, spoils if you want. You have to, you obtain in the dark matter, but you in some sense give up the asymptotic freedom. Okay, so, but as I showed you, there is also the other part of parameter space where we actually don't have the axion as a dark matter. In that part of parameter space, the axion is there and it gives you a contribution to the dark matter, but it's not large enough. So we need in that case to have something else to make up the rest. And in this model, one thing which is relatively simple to arrange is to have the right-handed neutrino to fill up the gap and give us another dark matter component. Now, for this purpose, we have exactly chosen, in some sense, one of the right-handed neutrino to be special and to actually not contribute to the mass of the light neutrinos. So the mass of the light neutrinos is generated only by 2 of the right-handed neutrinos. And this, the first one, we call it N1. We could have called it also N3, but or N2, but we decided to call it N1. Is the one which is has a different charge than the others, and therefore cannot have the Yukawa couplings like the others. Instead, it has just a coupling to the ZX, so the gauge symmetry, and it has again a mass generated by a neuronormalizable operator as the others. Now, this field, therefore, can be again a field in the TV range of mass and has a coupling, which is a gauge coupling. Nevertheless, it cannot really be a WIMP in some sense. You cannot be it because the couplings are usually suppressed. And in this case, the suppression comes, of course, from the Planck scale. In this case, if you take the gauge coupling to be relatively large, you have then that the mass of the ZX is pretty high. And then you have again that all the scatterings mediated by the ZX are actually suppressed. So in that sense, you cannot really generate the dark matter density as a WIMP in this case. You need to go to a different mechanism, and the mechanism we decided to use, which is natural for a particle which couples very weakly, is the feebly interactive massive particle type of mechanism, so the FIMP. So in this case, then you have actually not equilibrium for this field, but this field is produced slowly by other fields which are in equilibrium. In this case, the only particle in this axion sector which is really interacting relatively strongly are the scalar fields, so the Higgs fields. And indeed, in this case, then the Higgs fields decay can produce this dark matter candidate. But at the same time, one thing which can also happen is what we call a super FIMP, is the fact that the Higgs produces the Z boson, and the Z boson, which is actually here, the density is relatively constant, just depends on the mass of the fields, then decays into the right-handed neutrino. And in this case, therefore, it decays very late and produces, so makes up the last part here of the density. And in this case, you can get the correct density for various values of the coupling and the masses. Here is the formula. So we also understood analytically exactly what happens in this kind of this super FIMP regime. And in this case, the important parameters are only the branching fraction of the Z into neutrinos and actually the masses of the fields and the vacuum expectation values. So the density is just determined by the parameters in the axion sector, even for the neutrino. And remember, the neutrino mass is also related to the waves of the scalar fields. So in that sense, everything is set by the FA, more or less, scale. Apart from, of course, you have a couple of Yukawa couplings in the mass and so on. But we took those, as I said, to reasonable values of 10 to the minus 2, 10 to the minus 3. Now, this branching fraction is really set completely by the charges and therefore by the number of fields. And it is actually of the order of 1/12 for most of the parameter space. And in this type of model, again, you have actually again that in order to have sufficient dark matter, you need a sufficiently sizable value of the waves. Because again, these masses are all proportional to the waves. So here, of course, you have the waves also in the denominator, but it is in part compensated. And you see it in this plot here where we put the wave and the mass of the field. We need practically, again, waves of the order of 10 to the 12, 10 to the 13 in order to get the sufficient density for the right-handed neutrinos. And in these red points are the points where you have exactly the density from both the sum of both contributions. Otherwise, in this part of parameter space, the dominant part, you could get the density from the Higgs, or in the other only from the for the decay of the Z. Okay. So I am actually already at the end. Well, last thing I have to comment on is, of course, the coupling of this axiom. For those, there is not actually much new in the sense that this is really a KSVZ model, only that we have more exotic fermions than in the classical model, you have only one. And this means that actually there is no coupling to the photons. The coupling to the photon direct is zero because all these exotic fermions have zero electromagnetic charge. But of course, we obtain the contribution coming from the mixing with the pion. And this is given by this expression. So it's actually a negative. Sorry, they cannot see the expression. Oh, no, but there you can see it. Okay, so maybe you can see it. But anyway, it's the usual KSVZ type of coupling. And indeed, actually, there is recent, of course, the ADMX experiment, which started to publish results giving constraints on this coupling. Also for the KSVZ, you see it here. So that would exactly be relevant for this model, apart from the fact that in most of the parameter space, we are not in this mass range, but with the mass range a little bit different due to this issue of the neutron dipole moment. And so the region where we have the dark matter in the model, it doesn't fit in this window that the ADMX is measuring now. But the other news is actually that ADMX is not only putting constraints on the coupling, is also now able to explore actually the region where the dark matter density is lower than the full dark matter density. So the axion density is lower. So I didn't put a plot, but they have a plot where they can go down, I think, to 20% the dark matter density. And in this model, of course, there is also a lot of parameter space where that would be the case. So not the 100% dark matter would be in the axion. And so if you start to have constraints there, you could also find some surprises to find an axion which gives you only 20% of the energy density of dark matter. Okay, so and here are my conclusions. So I, of course, showed you again this old story about the Peche-Quinn solution for the strong CP problem, which of course usually relies on having a fully conserved global symmetry. This is usually, as I said, could be violated and should be violated by gravity. And in that case, you have additional operators which would, in some sense, give you back the electric dipole moment. But of course, you have to suppress those operators so that they don't violate the present bounds. And in any case, this is requires additional model building. So in the model we showed, as I said, we obtained this by having these particular charges and also a larger number of fields. But nevertheless, the ADMs we predict is usually larger if you want than the ADMs you have in the standard model, even if it can be way below the present bounds. And in this case, there is a little bit of tension between these values of the scale FA and the dark matter, if you want, density. So in some sense, in many cases, if the number of fields is too low, you are not able to have the axion as a dark matter candidate. And in that case, as I said, the neutrino can actually play the role with, again, a density determined just by the axion parameters. In this model, we didn't look at the baryon asymmetry of the universe, but of course that would be also a possibility, and we are still thinking about it. Of course, there is the possibility of generating that again from the neutrinos, even if they are relatively light. But maybe also the axion could play a role because, of course, it could also have, in this case, for example, in the evolution of the universe, also contribute. And that's it, actually. Thank you.
Thanks, Laura. Questions?
So in this model, the EDM of the neutron only arises through that delta shift in the
Yes.
So there is no other dimension 6 operator or that you induce?
Well, you can have higher dimensional operators. So we didn't check all the higher ones, but this one is the lowest order operator, which is a singlet. So we could have higher order. So the higher order there are even with the higher powers of the fields. And we didn't classify all of them. But there are no dimension 6, no dimension. So at least if you choose the charges as we chose. So this one is the lowest dimension operator you can write. And in some sense, this one is always there because this combination of charges correspond to one of the anomaly cancellation conditions. So if you want to cancel the anomaly, this operator has to be a singlet.
More questions? Yep.
Yes, these 10 exotic fermions, these are essentially sort of quarks, and they must be extremely heavy, that otherwise we would have seen them in Alice
Yes.
or anywhere, something like that. So what is their scale?
Well, in the model, we didn't fix it completely, but the scale is usually the VEV, the FA.
Okay.
So they are
okay.
usually,
Yes,
if you take Yukawa order 1, they would be exactly at FA.
Yes.
In principle, you could play around with them and make them lighter, but we didn't do that also because they are a bit dangerous for cosmology. So we don't want them actually in this, I have to admit, in this model, they are practically stable, so at least some of them, because there is no channel for them to decay. So in that sense, we are actually looking at the scenario where they are so heavy that they are not really produced in the early universe. So that you would be have this Pechi-Queen symmetry broken from the start, more or less, and these fields are so heavy that they just play the role in some sense of giving you the anomaly, but they don't really appear as dynamical degrees of freedom in the early universe.
And maybe another question, we were searching for this coupling of the axons to the quark, so to say.
Mm-hmm.
Wouldn't that also appear there in this model, that you kind of have an oscillating EDM finally as an observable too?
Yes, of course. I mean, this would be exactly the same as the KSVZ. So through the GG tilde. So the GG tilde coupling is there. If you want to, you can again rotate it into the mass of the, and so you would have an oscillating EDM as in the usual case. So this would be there as well. But the only difference is, of course, here you would also have a 0 order, so a contribution which is different from 0. But on top of that, you will also have the oscillation, and of course, well, in this sense, depends a bit on which parameter range you are, because of course, if you are in the case where the dark matter is, you don't need the dark matter solution, then the oscillation could also be smaller than usual in some sense, and then it would be also more difficult to detect.
More questions? Okay.
Hi, would you have in general isocurvature problems if you consider an inflationary sector? Then
well, yes, in principle you could, but you can have the scale of inflation sufficiently low. As I said, we need the scale of inflation low anyway in order that the heat temperature is not
yes.
high enough to generate these fields.
Okay, yeah, thanks.
Yeah.
So these exotic sector with its Yukawa couplings could in principle have also CP violation on its own device,
yes,
which is suppressed by the high mass scale. But I mean, how would you estimate the contributions to EDMs?
from these masses.
Yes, yes. So that.
Oh, wow, we didn't look at that. Well, in principle, it should be argument determinant of this mass is similar to the other quarks, I guess. So yes. So the theta is usually the, if you could have, I mean, the CP violation in the CKM, in that sense, you have one phase only, which is connected to this argument of determinant of the mass, which contributes.
Right. I mean, one would have to look at the sector, how many field redefinitions you need to make, or what are the CP rephasing invariants, and they can come with certain powers. But of course, it would be interesting to see what powers there are. And I don't have an intuition about how much suppression one needs for certain mass scale.
Another strong CP problem on top of it from these.
Well,
yes.
not a strong CP problem, but just a source of CP violation. And of course, yeah, we know that as a CP rephasing invariant, the Sialskog invariant is requiring these 2 generations at least of fermion masses. So it could be similar in this case, but I think it might be interesting to look into
in this case, we have also 10 fermions. So at least, of course, the 2 sectors are separate Yukawas because they have separate symmetries, separate charges. So in that sense, yeah, but these chi fields are all together in some sense. So if you have chi and chi equal to 9 or 10, you have 10 fields. So you have 10 by 10 matrix. This means that indeed you would have a lot of charge of not only a lot of mixing angle, but also a lot of phases there. And if I remember correctly, what is it? N plus 1 times n times n plus 1 divided by 2 or something like that is the number of phases. So it's indeed, it could be a lot of phases there.
Right, thank you.
Yeah. But actually, the theta combination is only argument determinant. So only one combination of the phases would play the role there for the theta parameter. Of course, the other phases could play the role in some other QCD processes in the sense. Of course, there is no direct coupling of these exotic quarks to the standard model quarks. That's also, we chose the charges also in such a way. But of course, if you have some loop diagram, they would enter probably nearly every where QCD is acting.
So I think we still have time for a couple of questions. I mean, if you want. So otherwise, I think we should thank Laura again.
Thank you.